Alright, students, welcome to the last lesson of our networks unit. This video will comprise of 9J and 9K, although 9K is more or less just questions, so there's no real tutorial for it, hence why I'm joining it with this video. So if you're going to do 9K, you have to watch this video. Now, the previous lesson, we learnt about your weighted graphs and how graphs have weights on them. So, for example, a graph will have a value on each of its edges, like so. Okay, and these values can represent weight, it can represent time, it can represent distance, but you need to read the context of the question to understand what the edge is talking about. In this chapter, for 9I, so the previous chapter, we learnt about finding the shortest path between one vertex to another. And there's two methods. There's trial and error, so basically just trying out different paths and seeing what might work. But then there's also Dijkstra's algorithm, which gives you the shortest path from one vertex to every other vertex. The only issue with Dijkstra's is it is a bit complicated to do, but I encourage you to watch the video that I did previously in order to do how to do the Dijkstra's algorithm. So please watch that. All right, let's get into 9J, the minimum connector problem, or in other words, spanning trees is what we'll be getting into. So in this chapter, you'll be looking at spanning trees. So let's read this. A minimally connected graph is one where removing any edge results in a disconnected graph, i.e. every edge is essentially a bridge. Now, what's that talking about is what in any minimally connected graph, you're trying to remove all the edges that aren't necessary to make the graph connected. Okay, and we'll see examples of that in a second. But basically, a minimally connected graph is basically n vertices. With n vertices has n minus 1 edges. So if you were to look at a graph, if it's minimally connected, it has to have the number of vertices, take away 1, and that will form the number of edges. Okay, so let's say, for example, you have a graph that has 3 vertices. Okay, for it to be minimally connected, you can only have 2 edges. Okay, because it's, look at the rule there, it's n referring to the number of vertices minus 1. So 3 take away 1 equals 2. Maximum 2 edges. So for this to be minimally connected, like so. So that's a connected graph that's minimally connected. Okay, so that's just an example there. A graph connected with a minimally connected graph with 2 vertices has only 1 edge. So let's say, for example, you've got a graph with 2 vertices, it's only got a maximum of 1 edge, and it makes sense with this rule because 2, which is the n minus 1, will equal 1 edge only. There it is. Okay, so that's what this is saying. If one vertex is added, only 1 edge needs to be added to make the graph minimally connected. So if I wanted to add another vertex, okay, and I only need to add 1 more edge for it to be minimally connected. So looking at that rule again, now I've got 3 vertices, 1, 2, 3, minus 1. So following that rule will give you the number of edges, which is 2. So in this case, I've got 2 edges. Okay. So some examples here. For each of the following graphs, state the minimum number of edges required that must be added to form a connected graph of some sort. So we need to state the number of edges that we need here. So for this graph here, and we might draw them as well. So I can see for this graph, I have 1, 2, 3, 4, 5. I've got 5 vertices. So remember the rule is n take away 1, where n refers to the number of edges. So 5 minus 1. That means this graph has to have 4 edges. And we can draw them here if we wanted to. So could go 1, could go 2, could go 3, could go 4. Okay, and now that graph is a connected graph of some sort, but it's minimally connected. Okay, I don't have any unnecessary other edges, for example, like having this. Okay, I don't need that. Okay, so it's got 4 edges maximum. Now that's only one example. You could draw it as this if you wanted to. 1, 2, 3, 4. All right. Any variation where it's got 4 edges will work. Okay, I might just leave one there. 1, 2, 3. Let's go crazy with it. And 4. Okay, there, connected. Minimally connected. All right, looking at this one. Okay, I've got how many vertices? 1, 2, 3, 4. So I've got 4 vertices. Take away 1, which means I should have 3 edges. Now in this graph, I only see 2 edges, so I just need to add one more edge. You can add it anywhere as long as, okay, if you think about it, I can't add an edge here. Why is that? Well, the graph is still not connected. You can see that this vertex and this vertex, and then this vertex and this vertex, they're not connected together at all. So this connection I've put down here for this edge is incorrect. I have to at least put that vertex, or sorry, that edge either there, or I have to connect it here, or I have to connect it here, okay, or here. Either of those will work, okay? It can't be like this. Although the rule makes sense, okay, it's got 4 vertices, minus 1 means 3 edges. I've got 1, 2, 3. It's not connected. It has to be a connected graph still. Remember, a connected graph is where each vertex is able to reach another vertex via different edges. Okay, this one here. So I need to have, remember there's 1, 2, 3, 4, 5. Okay, so if it's 5, take away 1, I should only have 4 edges. Now, let's count this. This is an interesting one because I've got 1, 2, 3, 4. Okay, so this is a crazy one because this graph has some interesting parts to it. This here, okay, is an interesting edge. It's a loop. Okay, a minimally connected graph cannot have a loop. Okay, you can't have this. So that's considered a loop. Also, a minimally connected graph cannot have a cycle like this. Okay, so technically, if I was to redraw this and make it a proper connected graph, I would draw it like this. Let's see. Let me see if I can get this going. Like this. So I'd get rid of this. Whoa, okay. That's not going to work. Get rid of this. And I'd also get rid of, let's see if I can draw a skinnier pen here. Get rid of at least this cycle. Okay, and I'd redraw it as, for example, I could go there. That's connected. So I've got 1, 2, 3. I need one more, and I could connect it here. Now that is a connected graph. Okay, compare it to the previous one there, where you can see that there's a loop that's disconnected, and you've got a cycle here. It's not a minimally connected graph. It has to be this. Okay, for it to make sense. All right, so just watch out for that. All right, let's keep going. Trees and minimum connections. So a tree is basically a connected graph with no loops, like I mentioned earlier. So a minimum spanning tree has no loops, no edges. Okay, that can be that can be defined in 3 equivalent ways. Okay, so sorry, it has no loops. It can have multiple edges. So the other thing I was saying that it shouldn't have is there's no cycles. You can't have a cycle. Okay, and the graph is minimally connected. So everything is a bridge, and between any pairs of vertices in the graph, there's exactly only one path. So what that's saying is between every vertex, there's exactly only one edge. Okay, you can only have one edge between each vertex. That's what this is saying. Okay, the graph is minimally connected. Everything is a bridge. Okay, that's pretty straightforward, and there's no cycles. So for example, let's say you've got a graph like this, and also no cycle. So let's say you've got a graph that looks like this. So this, for example, is a cycle. Okay, because it cycles like that. This, no good. Okay, you don't want that. No good. And there's no loops either. So what you want, so remember a loop looks something like this. Let's say you've got your vertices, got your graph. Oh, let's draw another vertex here, sorry. Connections there, but then you might have one vertex that has this. This is a loop. Okay, you want none of that. No loops allowed. Okay, no loops. Since a tree is minimally connected, okay, remember a tree will always have a minimally spanning tree will always have n minus 1 edges. So the number of, remember n refers to vertices, okay, n refers to vertices minus 1 will give you the number of edges. So every graph must contain a tree, including the case where the entire graph is a tree, obviously, okay? So in this example here, every graph must have a tree. We're going to find a tree in this graph. So what you want to do is when you get a question like this, always start by drawing your vertices first. Doesn't have to be in order, but what I like to do is sort of draw them in a similar position to the graph itself. Okay, and what we're going to do is draw a tree here. Now, if you want, you can pause the video and try and draw your own tree. See if you can get a tree from that, but you can also watch mine if it's a bit confusing still. Okay, but I'm going to draw a tree here for you guys and see if you guys understand. So remember, a tree, you have to follow those rules. There's no loops, no cycles, okay, and every single vertex must be connected. So let's start from 1. So I could say that 1 is connected to there, 1 is also connected to 3. One thing I'm doing is I'm making sure that I adhere to the vertices that the graph already has. Okay, so for example, I'm not going to add a edge from 1 to 4. Okay, because 1 to 4 does not have any connections at all, no direct connections. One thing I forgot to put is labels here, guys, so I'll just put that in here for you. 3, 4, 5, and 6. Okay, so you want to make sure that you adhere to the original graph and the connections that it has. You don't want to add your own connections. Like for example, 2 to 5 does not have a connection, so you don't draw one there. Okay, don't draw an edge there. All right, what else can we do? So I might go 3 to 6, and then 6 is connected to 4, and 3 is also connected to 5. Okay, so there's my minimum spanning tree for that. Now that is only one example of the multiple spanning trees that you can have here. Let me draw another one. You know, again, I could go 1 to 2, but this time I might go, well, I could include just 2 to 3, and then the connection between 1 and 3. Okay, if I included the connection between 1 and 2 as well, this would no longer be a spanning tree, because I can see a cycle here. So you can't have that, no cycles. All right, I might connect from 3 to, let's see, 4. 4 can connect to 6, and 6 can connect to 5. Notice how this tree looks different to this tree, but both of them are correct. Okay, because I've adhered to the rules that the graph has. There's no loops, no cycles, and it's connected. All right. So there's other examples and multiple other examples you can put in here, but those are just 2 that I will include for this one. Okay, so there's more than one answer actually, or more than 2 in this case. All right, spanning tree. So a spanning tree is a graph. This is a weird one. A spanning tree in a graph, is a graph that includes every vertex of the graph. Okay, essentially what we've done here. Okay, so a spanning tree is going to be a graph where every single vertex, okay, is included in there, but only using a tree. Okay, similar to this, kind of like a branch. Okay, again, remember the rules: no loops, no cycles, and everything has to be connected. So for example here, you can't have, for example, this, okay, because that creates a cycle. It has to be minimally connected. So let's try this. Consider this graph. Give me an example of a spanning tree. Okay, so let's say you have A, B, C, D, E, F. 6 vertices. Always label your vertices, guys. All right, so let's draw some spanning trees here. Here I can see you can go from A to B. That'll work. B to F. Yep, you can put that in. So again, I'm adhering to the connections that the tree will have. I can go B to E if you want, B to C, and then E to D. Okay. Now remember the rules here. If I wanted to figure out how many edges this needs to have, remember you've got 1, 2, 3, 4, 5, 6. So 6 take away 1. I should have 5 edges. So that means in this graph I've got 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5. And so I've done it correctly. Okay, I could do another example here if you want of another spanning tree. Again, make sure you draw your vertices first. And remember the rules for your spanning tree. So you can't have a loop, you can't have a cycle, and everything has to be connected. Okay, it has to be. If it's not, if you don't connect everything, then it's not a minimum spanning tree, or not a spanning tree. All right, so let's draw some connections. I might remember I can only have 5 edges. Yeah, so looking at my connections, I might go C to D. Give a connection there. D can connect to F to B. A can connect to F. B can connect to A, and then E can connect to B. That's 5. 1, 2, 3, 4, 5. You can only have 5 edges. Okay, so next part. From this graph, what are examples of trees that are not spanning? So not a spanning tree. Okay, so again, let's draw my edges, my vertices, sorry. So A, B, F, E, C, D. Okay, that's F. So examples of trees that are not spanning. So you can do many examples here, but remember the rules for a spanning tree. Yeah. So for example, I could go looking at my connections here. I can go A to B, and B to F, and then F to A, or A to F. See, this is already not a spanning tree. All right, and you can see why. Okay, for this, okay, there's 2 things that are wrong here. Why it's not a spanning tree. I can see, all right, I'm going to circle them for you, that here you've got a cycle. So it's not a spanning tree. Okay, not spanning. Okay, so it's not part of the spanning tree rule. And the other thing that's wrong here is this, multiple edges. Between vertices. Okay, so obviously not part of the spanning tree rule. Yeah, that's why it's not spanning. I could do another example. For, could add another one actually here. Let's say here. What's happened here? Well, there's a loop. Okay, no longer a spanning tree. Okay, or I could even go one step further and say, boom, there, look at that. What's happened? Well, it's no longer connected. Okay, there's no connection there. So this is a example of probably the worst graph you could ever have. Okay, there's no connection here. I'll put that in here. Not connected. So this is an example of a spanning or non-spanning tree. Okay. All right. Part C. This one's a bit tricky because we haven't really covered it, but examples of spanning subgraphs that are not trees. Basically, what a spanning subgraph is more or less a graph that's obviously built off the original, but what you need to have is all of the vertices in that graph. Okay, so let's say, for example, You've got A, so I'll redraw all of my vertices, A, B, F, you've got E, C, then D, A, B, F, F, you've got E, C, D. So basically a spanning subgraph, let me just get that here again, so I don't have to keep scrolling up and down. Alright, so here's my original graph, right? Spanning subgraph is basically a graph where it includes the same vertices in the original graph, but it's also a tree within it. But there's something, there are some rules that we haven't adhered to. So say for example, I've got A to B and then B to F. This already in itself is technically a spanning subgraph. So it's basically a graph within the graph, and it's basically a spanning tree. Yes, this thing is a spanning tree, but obviously it's only a subgraph, and for it to be a proper spanning tree, so as in a proper full tree, obviously you have to adhere to the rules. It's not connected, so everything else has to be connected. Another example could be, I've got C to D, and maybe F to D. Then I might have like B to E, B to E, and then I might have E and F connected. That's a spanning subgraph. Okay, it's a subgraph within the original graph. Okay, but it's so it's spanning, but it's not a tree because it doesn't include A. Okay, so that's basically what a spanning subgraph is. That is not a tree. All right, so let's look into minimum spanning trees. So the weight of a spanning tree is the sum of the weights of its edges. So this is sort of what we've been building up to, your minimum spanning trees. A minimum spanning tree is a weighted graph where the spanning tree has the least weight. So what you want is you want to have a tree such as this, okay, built off the original graph, but with the minimum weight of edges. So if you can't remember, or if you don't understand what that means, watch the previous video for understanding what weight is. There's two methods for finding a minimum spanning tree: Kruskal's algorithm and Prim's algorithm. There may be multiple trees as well in a single graph. Each of these spanning trees may have the same weight. Okay, so that's something to think about. There's actually, what this is saying is there's multiple answers in each graph. Okay, that is multiple trees within a graph that you could have, but the main thing is they have to have the minimum weight. And there's two algorithms that we're going to learn today. All right, let's do the first one. So minimum spanning tree for Kruskal's algorithm. What you need to do for this is you need to delete all the edges, and then from there include an edge of least weight. Repeat step 2 until a cycle is formed, unless a cycle is formed, so you can't have a cycle. And if step 3 can no longer be completed, a minimal spanning tree has been found. Again, there may be multiple ways of doing this, okay, or multiple answers in here. But at the end, you need to find the minimum spanning tree. All right, so how do we do that? How do we do Kruskal's algorithm to find a spanning tree in these weighted graphs? So let's do it. All right, so what you have to do is, again, start off by drawing the vertices. I always start with that. So P, then Q, then R, S, then you've got T, and then you've got U. So for this, what you need to do is start off by finding the edge with the smallest weight. Okay, so that's what I'll like to find the edge with this. Oh, also, don't forget, label your vertices. Probably a big deal, so make sure you label them. T, and that's U. Okay, all right, so let's find the edge with the smallest weight. Well, I can see from this graph, R to S is the smallest, so I'm going to include that. I like it. It's really low, so R to S, and the weight for that is 18. All right, next I can see Q to T. That's really cute. Oh, that's really good. QT, 20. All right, got a really good, nice light weight there. What else is there? I've got, okay, 25, therefore Q to S. All right, let's include that one. 25. Okay, so now that I've got this, remember, you cannot have any cycles like that or like this, okay? Because that then means it's not a spanning tree or minimum spanning tree anymore, okay? What else can I do? Well, 28 there is pretty good. So I might include that, U and T. All right, the last one is I need to get P connected somehow. Now, if you look at the edges for P, you've got 38. So P to Q is 38, or you've got 34. I would think that 34 is probably better. Okay. And what I've done here, okay, so I've actually now 28, there's 25. I've only included in this, using this algorithm, the edges with the smallest weight. Now, why haven't I included 29, okay, or this one here? Okay, because if I put that in, it's going to create some sort of a cycle here. And if you think about it, if I kept that but then got rid of this, well, 18 is a lot better, isn't it? It's a lot lower than using 29. So I don't like 29, it's too high. Similarly, with all the other vertices, edges, they're all quite high. So for example, U to S is really high. You don't want to include that. Remember, you're making a spanning tree here. Minimum spanning tree. So you want to include only the smallest ones. And that's it. Really easy. Pretty straightforward, I would say. So that means the total weight for this minimum spanning tree, I forgot to put that here. Okay, so the total weight would be 34 plus 28 plus 20 plus 25 plus 18. Okay, so put that in your calculator. 34 plus 28 plus 20 plus 25 and then plus the 18 will give you 125. So that's the total weight of this. All right, let's try this one. All right, this one's a bit, it shouldn't be too hard, okay? But again, start off by putting in your vertices. M, N, you've got R and S here. You've got Q, let's put some space between some of these, hey? Q, P, and then O. Make sure you label them. L, M, N, O, P, Q, R, and then you've got S. All right, so let's draw our edges here. Again, starting off with the smallest weight. I can see R and S are quite, there's a really small edge there, so I'm going to include that. 24. Next one, well, I can see, I think the smallest one would be 31 between M and S, so include that. All right, what else can I see here? This 35 is pretty good. Might include 35. So as you can see, what I'm going is from lowest to highest with the edges, guys. So look for the smallest to highest edges, but make sure you don't create any loops or cycles. What's next? I can see M and N have a pretty good edge, so put that in. 38. And remember, to adhere to the rule, you got to make sure that your graph is connected. So you can't have any vertices that are by themselves at the end. Alright, so I have to connect Q, P, and O still. Where am I at? N. Let's see. Q and P. 55, 63. Well, S to P has a pretty good connection of 50. So I might include that. Okay, I like SP. It's good. Although, actually, no, I think I may have found a better one. That's not as good. I think R to P is better. Okay, so look at the weight. Look at that weight. R to P has 47. Okay. Let's see, what else? We could go P to Q. Okay, it's better than R to Q. You can see it's less. So let's connect them two. And then O, okay, you've only really got two options for O, 72 or 63. I would rather go with the 63, okay, because it's less. And you can see now all the vertices are connected and there's no loops, no multiple edges, or no cycles. Okay, so that should be the minimum spanning tree for this graph. Okay, notice how I again included some and not the others in terms of the edges. Like 40 is pretty good, right? But if I include 40, see how it's included a cycle now, okay? And also if I get rid of the other ones, not as good. I prefer the 38, it's less. Okay, so let's put that one back. All right, so let's add the weight for this. So 35 plus 24 plus 31. Now this is where some people trip up, yeah? Make sure you add all the numbers. Double check your calculators. Don't skip on any numbers, please. Plus 63, oops. Rewrite that, it's quite ugly. 55, 63. Okay, so 35, 24, 31, 38, 47, 55, 63. Good. Make sure you add all the numbers properly. 35 plus. In your previous SACs, guys, people were putting in random numbers in their calculators. And I know because your working out was correct, okay, but your answers were wrong. 55 plus 63. So that should be a total weight of 293. Okay, and that's how we do Kruskal's algorithm. Now we'll get into the final part of this lesson, okay, which is minimum spanning trees of using Prim's algorithm. So similarly, you start off by getting rid of all edges, and then number 2 is you start select any vertex and call this vertex visited, and then every other vertex is unvisited. So now what we do is from any visited vertex, add a least weight edge to that adjacent unvisited vertex. Repeat step 3 until there are no unvisited vertices left. And if step 4 can't be completed, a minimum spanning tree should have been found. Now, this is actually quite similar to the Kruskal's algorithm. But here what you do is you start off at one vertex and you sort of go from there. Okay. So let's use this as an example. I'm going to show you how it's done. So for this one, the vertices are not labeled. That's fine. Okay, but the idea is still similar. You have to start off by drawing your vertices. Okay, so there, there, and there. Oops. Start off by drawing your vertices. All right, so let's go. Start off at one edge. Okay, I'm going to start off from this edge. Okay, so I can see that it has a connection there, and it's 12. So put that in. So from there, I've got to connect to these two vertices, either one. I would prefer to probably connect to the one that has 14. It's got a lesser weight, so 14. Okay, I'm here, this edge here, a vertex. I have to connect to either of these two. Oh, sorry, any of these, really, whatever I can connect to. So I've got a connection here where it's 12, so I might include that. It's actually pretty good. It's better than this connection here, 15. Don't like that, okay? So I'm here, okay, back here, I still need to connect to another edge, vertex. I can see that here, this, okay, has a connection of 11, so that's pretty good. I like that. What else? Well, from here, okay, I'm going to keep this edge here. This is really good. It's only 9. That's good. Last is this one here, this edge, vertex. It's not connected yet, okay? I can either go from get the 16 or the 18. I think I would rather get the 16. Okay, that's 11. And there you go. There's my minimum spanning tree for that graph. And then from there, add the weights. So you've got 12 plus 14 plus 12 plus 11 plus 16 plus the 9. Okay, and get your calculator out. I think the good thing about this topic, guys, is you don't technically need a CAS. Just a normal calculator will do. 16 plus 9. Okay, that equals 74. So the minimum spanning tree weight should be 74 for that one. All right, let's keep going. Next question here. Oh, this one's a bit trickier. It's got a lot more vertices and edges. All right. What you can do, actually, no, yep. What you can do is, I think some questions you will get a chance to actually just scribble out certain parts or certain vertices and edges, but I'm sorry, certain edges, but we'll go with the way that we've been learning so far. So let's just put in all, and this can get a bit hectic, I know, but let's put it in. So you've got that 1, 2, 3. You've got this one here, down here. You've got one up there. Yeah, you can see that I'm not drawing it to scale, or exactly to scale, but that's okay. Just got to make sure you have the correct amount of vertices. Okay, so I can start off at any vertex I like. I might start off at, I'll start here. Let's just start there because I'm already here. So I can see that this connection here is pretty good, so I want to include that. Next, I need to connect to, well, this vertex can connect to there or there. And I think I would prefer to connect to, let's see, probably here. Probably definitely better, I think, than the 25. That's good. All right, where else? Where else can I connect? Well, I was down here. This vertex can connect to there. That's quite high. I am here. 25. Yeah, I think 25 is probably the better option. So I'm going to go 25. So I'm there now. Okay, good. Now I'm up to here. All right, so I need to connect to, oh, this vertex here can connect here, 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 or here. So let's look at all the possible connections here. I do like the 14. That's pretty good. So I'm going to connect to that. One thing I forgot, sorry guys, make sure you put in your weights so you don't get confused. That's 21, that's 14. Okay, let's see. I do like, what else can I connect to? 16 is pretty good. Okay, that's 15. I think I will go with 16 right here. Okay, that's pretty good. Let's see. Down here, what else can I connect from here? I've got 15. I've got 18 as well there. I think I'll go with 15. Okay, there. So I'll put 15 here. And here you've got 17, which I think is pretty good. All right, so from this vertex to that, well, it's 23. It's quite high. And then you're up to here as well. You've got, I can connect up to there to get 20. That's pretty good compared to 25. So 20 is pretty good. That's 29. It's quite high. That vertex to that is 25. So that's also quite high. I could go from this vertex to there. It's 34. It's quite high. So I think the best option would probably be this connection here, which is 25. Okay, last are these two. So for this one, well, I can see 19 is pretty good. So let's go with that, 19. And the last one is 21. Here is probably the best option compared to, well, that is my only option from here. So there, 19, 21. And there, I would say, is my minimum spanning tree for this graph. And then from there, you would just add your weights, which is going to be 13 plus 21 plus 25 plus 14 plus 16 plus 15 plus 17 plus 20 plus 25 plus 19 plus 21. Okay, sorry, it's going to move this. Oh, I can't. Let's move this way then. So I've got 13 plus 21 plus 25 plus 24, 16, totally missed one. 14. Just make sure I got them all. 13, 21, 25. Oh, okay. 14, 16. And this is where people trip up. So double check your numbers. 16, 15, 17, 20, 25, 19, and 21. So minimum spanning tree for that, or the weight, the minimum spanning tree weight for this is 206. All right, and that's basically all for chapter 9J and 9K. So make sure you watch the whole video, guys, to do both chapters 9J and 9K. Hope you learned something. If you have any questions, please ask me. I'm more than happy to help. Thank you.